Hi, everybody. Welcome back to Chemical Principles. We really need to find a title for this. I don't know. We'll figure something out. I don't know how much longer, but yeah, we'll figure something out. We were not here on Tuesday because even though it is not, I personally believe that Election Day should be a federal holiday. So I did decide that we had no classes. There is something very satisfying about putting on a class without having the oversight of a bunch of people who have no idea what education is all about. And yes, I'm talking about administration, and I'm talking about Board of Regents. Anyway, so yes, we were not here on Tuesday. If this upsets you, please feel free to let me know. I will be more than happy to refund all of your money. We are getting close to the end here. We have about 3 weeks left, and the only reason we have 3 weeks is because I've also scheduled for Thanksgiving off, November 24th, which is 2 weeks from now. We are on schedule today. We're going to talk about equilibrium, which is related to kinetics. So actually, we are going to begin talking about kinetics, and then we will get to equilibrium. If we fall behind, it's fine, because we are actually ahead on redox reactions in electrochemistry, because as you may recall, we talked about redox reactions back when we were talking about reaction types. So that'll be more or less a review. The last 3 lectures are basically beyond the scope of regular chemistry. This goes into nuclear chemistry, just to give you a little bit of a fundamental understanding of that. Then we have a couple of special topics days that we could actually cancel those if we don't need them. They are there in case I fall behind. This close to the end, I doubt that I will. But it's still possible. I may need one of those days to make up a little bit of time. But if not, then we either need to decide what we want to learn on those 2 days, or we can cancel them. Go either way. And if I cancel them and that upsets you, let me know immediately. And I already told that joke today, so we're not going to worry about that. Tim, you have any diamonds?
Diamonds?
Diamonds.
Yeah.
Do you?
Yes.
Are you wearing them now?
No, not at the time.
Okay. Diamonds are a really bad investment. Because, actually, and I should ask you to run and grab one real quick, but it's okay. We don't have to. If you look really closely at those diamonds, if you look really, really closely, and I'm sure that when you first got them, you probably looked at them pretty closely. If you start seeing them becoming discolored, if you start seeing, now, every natural diamond has flaws, but if you start noticing additional flaws, like little black specks in it or anything weird like that, there's a reason. It's because thermodynamically, one can prove that the conversion of carbon from the diamond allotrope to the graphite allotrope, which is what's in lead pencils, that's graphite, that occurs naturally. That is a spontaneous reaction going from diamond to graphite. So your diamonds are changing into graphite. They're going from precious diamonds to worthless graphite. It's not worthless. I mean, graphite actually is also a really good lubricant. So keep an eye on your diamonds. And you might start noticing some changes in, I don't know, 3, 4, 5 million years. There's a distinct difference between if a reaction is spontaneous or not and how quickly the reaction occurs. We talked a little bit last time about catalysts. You can always find catalysts because they're being chased by the dog lists. A catalyst can speed up a chemical reaction, but cannot slow it down. That's because it provides an alternative pathway for the reaction. We talked about reaction mechanisms last time. And the example we gave was carbon monoxide being converted into carbon dioxide, something that does occur naturally, but very, very slowly unless there's a catalyst present. Catalysts, such as in your catalytic converter, which is really just strips of copper coated with platinum, provide a new pathway for the reaction to occur. And the reaction occurs more quickly than without it. If a catalyst provided a pathway that was slower than the original, nature would just choose the original pathway. It would still have that original pathway available to it. So that's why catalysts do not slow down chemical reactions. So today we're going to talk a little more about equilibrium. No, we're going to talk about kinetics, and then we're going to talk about equilibrium because equilibrium is very much related to kinetics. My little pad turned itself off. Okay, so now I need to start sharing it again, which means I need to do that. Then I need to do that, and then I need to do that, and then I need to do that, and then I'm there. The example that we have been using for, now if you recall in classical thermodynamics, we've spoken of really three terms, four if you include the zeroth law. That one introduced heat. But the three that we speak of most frequently is enthalpy, which is the heat of reaction, whether or not it is exothermic. We speak of entropy, which most people think of as disorder, and it's fine to think of it as disorder, although we did decide, probably better thought of as lack of knowledge or lack of information. And then we did Gibbs free energy, which is work energy available for work. Let's try this in English. Gibbs free energy determines whether or not a reaction is spontaneous. So the reaction that we did, if I'm remembering the stoichiometric coefficients correctly, and any reaction will actually work. This is just a nice little sample reaction. Is this. So if we make up an artificial graph, this is an artificial graph because we're going to put reaction pathway, which it does not have any real numbers associated with it. So we're going to put the reaction pathway along the x-axis. We're going to have reactants on the left, products on the right. And we're talking about heat of reaction, so we're going to put enthalpy. We're going to use kilojoules per mole on this side. A joule is just a unit of heat, just like calorie. We've defined calorie. It's the amount of energy required to raise 1 gram of water 1 degree Celsius. If I'm remembering correctly, there are 4.184 joules in 1 calorie, but I may have it backwards. So if you need that conversion factor, look it up and make sure that I'm correct. Now, last time, here it is. We calculated delta H. Remember, it's always products minus reactants. So our reactants for this reaction, this is the same reaction. You can see it here, although it's at negative 15 degrees Celsius. The reactants had an enthalpy of positive 74.81 kilojoules per mole. And that was the reactants. So we can actually put that on the graph. 74.81. Our products, on the other hand, had negative 877.145. Kilojoules per mole. By convention, we always put the reactants on the left, the products on the right. So we actually have we can write them in if we like. I'm leaving out the states for this because I'm getting a little cramped for space. Now, when we draw a reaction diagram like this, because the reactants are higher than the products, this is exothermic. And the total amount of heat being given off, which we've already figured out, so we may as well just look it up, negative 802.335. Kilojoules per mole. Now, if this was an endothermic reaction, that would be just the opposite. The products would be higher than the reactants. But we've talked about this before. Don't write this down, if our reaction pathway just simply looked like this, there would be nothing to prevent this methane from just reacting with oxygen first chance it gets. There has to be a barrier there. There has to be something that is keeping this reaction from occurring immediately, not spontaneously. We have to be a little careful with our terminology here because this is a spontaneous reaction, but it doesn't occur on its own. It needs something else. Well, this is methane gas. What it needs is a spark. It needs some form of energy input. So there's a barrier here. Preventing this reaction from occurring spontaneously. We call this the activation energy. The activation energy. This is the amount of energy you have to put in to get this reaction started. Now notice that as you put this energy in to get the reaction started, you get the same amount of energy out on the other side. So this does not contribute to the total reaction of the total energy of the reaction. This is just the energy required to get it started. Once it starts, then of course it has even more energy to keep going. That's why it's just to get it started. Once it's started, it generates its own energy. Some years ago, do I have time to tell this story? I'm going to tell the story anyway. In a chemistry lab, we were using glowing splints to test gases given off from reactions. And the reaction we had going was, if I'm remembering correctly, hydrogen peroxide with manganese dioxide as a catalyst. And you take a little hydrogen peroxide, you put a little manganese dioxide in there, and it starts fizzing and bubbling. And you test it with a glowing splint. Well, all a glowing splint is, it's just a little piece of wood. You light one end on fire. You hold it by the end that's not on fire. Sometimes you had to tell students this. You would blow out the flame. So the splint was still glowing. So it was like a glowing ember. And basically you use that glowing ember to test the gases coming out of the test tube. And one of three things can happen. It can go out. Done. If it goes out immediately, that's carbon dioxide, just snuffed to the flame. Or it can reignite, sometimes with a little pop. If it reignites, that's oxygen coming off. Or it can explode. Now, when I say explode, we're just having a little bit of hydrogen. That means hydrogen. Just enough in there to make a nice loud pop. Not enough to do any real harm. So the student said, I've never done this before, and she wanted me to stand over and watch her as she did it. And I said, okay. So she's holding the test tube here, and she lights the glowing splint, and she puts it over, she blows out the flame. I said, okay, now just put the glowing splint over the top of the test tube, which she does, and the flame reignites. And I start to explain to her, okay, that means there's off, and it's about that far that I got when she went, and the glowing ember went down into the test tube. The heat sped up the reaction. The increased reaction rate ignited the back of the glowing splint that was inside the test tube. So there's like a little gap. So you couldn't just grab the glowing splint. And she created the most gorgeous blowtorch I'd ever seen. She had a flame about an inch high, just this gorgeous blue flame. And you can't cover it up, because in labs, if there's a fire, you usually just put something on top of it. No, it's making its own oxygen. That's not going to do anything. And of course, she's freaking out. And this is the kind of professor I was. I just thought it was hilarious. And I knew, you know what, as long as nothing really happens to it, if we don't panic, it'll burn itself out eventually. So I take the test tube from her and I start talking about what's going on. I'm just holding on to it, waiting for it to burn out, because there's not much else I can do. It was wonderful. And what that had to do with what we're talking about here, I have no idea. But that glowing splint, the activation energy was in the glowing splint. There was enough heat there, and because of the wood was the fuel, it sort of acted as its own activation energy. And as the reaction was occurring, more and more heat was coming out of it. It became a self-sustaining reaction. That's what we mean when we say spontaneous. Now, there are endothermic reactions that are entropy driven. such as ammonium chloride. If you dissolve ammonium chloride in water, this is a spontaneous reaction. The ammonium chloride will dissolve, but it is extremely endothermic. So it might have now here I have to put the states down. This is what this reaction profile might look like. So now energy is being absorbed by the reaction. So this would be an endothermic reaction. All right. So let's take a generic reaction. Actually, I'm going to put stoichiometric coefficients here. The stoichiometric coefficients I'm going to put as lowercase. The reactants and products I'm going to put as uppercase. Let's assume this is exothermic. We're going to look at this. So it is exothermic. And we have our activation energy here. What I have not been putting up here are funny little stars like this. That star represents a transition state, is what it's called. The transition state. We've spoken about this before. When we went through and talked about carbon monoxide, for example, we talked about the possibility of creating this complex CO3. It is not a real compound. It does not exist. But it's somewhere in between the reactants and the products. Bonds of the reactants are beginning to stretch and weaken. And you're beginning to form new bonds that you're going to see in the products. But it's not quite there yet. It's this complex that does not really exist. It's an intermediate. It's not real. Well, I mean, you can't isolate it. That's what this activated complex really represents. This transition state or activated complex this is that thing that kind of exists just a flash of an instant, not even a full instant, just a fraction of an instant. Just it's somewhere in between the reactants and the products. And chemists can measure the actual value of activation energy. And they used to actually, Back when I was teaching, we had one of these. Chemists used to take big blocks of styrofoam, big blocks. Actually, the one I had was about this big blocks of styrofoam. And they would literally take spoons and carve out the reaction pathway, where on one end, the height, and they would create this pathway, and on one end, the height or the depth that they dug into their styrofoam bowl corresponded to the actual enthalpy of the reactants. And then there'd be this hill, which corresponded to the actual height of the activation energy, and then down to the valley below, which was the actual enthalpy of the products. And they would literally, this was way before the days of computers, they would literally take marbles and roll them along these pathways to kind of see how the marble flows, to see, well, geez, does it favor going this way or does it favor going that way? And it was completely unrealistic, but it was a lot of fun. This activation pathway is related to kinetics. Kinetics is simply how quickly a reaction will occur. So let's talk about how quickly a reaction will occur. So here we have a reaction. Every reaction has a reaction rate law. I say reaction rate law, and they all look the same. Like this. Now, in chemistry, the square brackets have a very special meaning. The square brackets represents not just concentration, but specifically molarity. If you recall from our discussion of solutions, molarity is a concentration unit, moles per liter. So square brackets always means moles per liter. K is the reaction rate constant. It's just a constant. We have to determine it experimentally. These two superscripts, and this is very, very, very important to note. These superscripts are not the stoichiometric coefficients. At least not necessarily. Sometimes they are the same, but when they are the same constants as the stoichiometric coefficients, it's just coincidental. It has nothing to do with the stoichiometric coefficients. How do you determine? See, now we have three things we need to determine to get the rate law. The rate constant, the rate law constant, and those two stoichiometric coefficients. Here's how chemists do it. They do a series of chemical reactions, and they vary the concentrations. and they measure the rate. The way that you can measure the rate, there are several ways you can do this. You can measure how quickly one of the reactants disappears. You can measure how quickly one of the products appears. You can do this using, for example, spectroscopy. You shine light through it. If one of the products has a specific color, then you measure the wavelength of that color and you see how quickly that color develops. That's all you need to do. An easier example, if you have a reaction where you're producing a gas, unless you're Mick Jagger, in which case it's a gas, 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 you take a reaction vessel to collect the gas, and you can measure how much gas is collected over a certain period of time. So how long does it take to collect 1 liter of gas? Thanks to the ideal gas law, we know how many moles that is. So you get moles per second, moles per hour, however long it takes. Usually you measure it per second. But you have some form of measuring reaction rate. The appearance of a product or the disappearance of a reactant. And you run a series of reactions. So let's say that the concentration, the molarity of A is 0.2, the molarity of B is 0.2, and the reaction rate is 4. The reaction rate is 4. Now you need to do this a couple of times. So maybe we're going to double the concentration of A. Now here's the key. In these reactions, you design them so you only change the concentration of one reactant at a time. So we're going to keep B at 0.2. And our reaction rate increases to 16. I'm pulling these numbers out of the air. Now suppose we wanted to now we need to figure out B. Now we don't have enough B to do it to double B. So let's take it half. And the reaction rate that we get is still 16. That's all we need. That's all we need. So our rate law is like this. So let's figure out alpha. And here's what we're going to do. We have two experiments where B is constant. But notice that we double A. So what we're going to do is take a ratio. Actually, I'm going to go the other way. No, we're not. Yes, we are. We're going to go the other way. So we have 0.4. We're going to put that on top. We do not know what that coefficient is. We do not know what that power is. But when the 0.4 gave us a reaction rate of 16, whatever the units might be. 0.2 gave us a reaction rate of 4. So what we end up with is 2 to the alpha is equal to 4. So now here's the question. What power of 2 gives us 4? Well, the answer is pretty obvious. Alpha must be equal to 2. Alpha has to be equal to 2 because 2 to the second power is 4. So now we know alpha. What about beta? Well, here we're holding a constant, but we're changing b. So we'll set it up the same way. (16) divided by 16 is 1. So what power of 2 gives us 1? Well, the only power of 2 that can give us 1 is 0. Any number raised to the 0 power is equal to 1. Okay? Any number raised to the 0 power is equal to 1. So now we have the rate law, and I wish I could have done this on the same page. Come on now. And we don't have to write b to the 0 because that's just equal to 1, or rate is equal to k times the concentration of reactant A squared. That's our rate law, but it's not quite complete because we still don't know the value of k. To get the value of k, we go back to our table and we can pick any one of these reactions that we want. So let's choose the first one. The first one, the concentration of A, well, actually, the rate that we got was 4, was it not? Go back one. Come on. There you go. So the rate is equal to 4. We do not know the reaction rate constant, but we know everything else. Should be 0.04, right? Here I am reaching for my calculator, and this is such an easy calculation because K is simply equal to 100. So now we know our entire reaction rate law for this reaction. We can find the reaction rate now for any concentration that we want, any concentrations of A and B that we want. This is kinetics. This is figuring out not if a reaction occurs or not, but how quickly does the reaction occur. As it turns out, that reaction rate constant will tell us what the activation energy is. And it's kind of an exciting thing. It's called the Arrhenius equation. And we're going to talk about it after a break. It is 10:38. Kim, how would you feel about, oh, it's 10:39. So what do you say we come back at 10:50?
Sounds good.
All right. I will see you in 11 minutes. That's not the one I wanted to push. Hang on a sec. Hang on. Cancel that. Yada, yada, yada. Oh. All right. So we have devised our first rate law. I don't know if you're ever going to need to do that or not. Probably not. But there are some important things that I want you to note. First of all, note that all rate laws look the same. The most important thing is that the powers in the rate laws are not necessarily the stoichiometric coefficients. And the reason is very simple. I mean, in this case, I gave an example. No, I didn't. The reason is very simple. If you have, well, either a methane or our carbon monoxide example, Both of those have 3 reactants. And there's no rate law that brings 3 reactants together simultaneously. It's always binary. There's always 2 reactants that come together. Or something starts to break apart, or 2 things come together. It's never 3. So, yeah, the stoichiometric coefficients do not factor into these rate laws. And the other thing that I want you to note is that's rate law constant, which is determined experimentally. Now, obviously, these rate laws depend on the reaction, obviously. They also depend on temperature. So if you change the temperature, you're going to change the rate law. But the thing that you change with changing temperature is the rate law constant K. Is temperature dependent. And the dude who figured out that dependency is called Arrhenius. Arrhenius gave us a very nice equation. I love the Arrhenius equation. It blows my mind. It says that the rate law constant K there it is. A is equal to EA negative E. It's this. So here's our rate law constant. This, oh, what the hell do they call this thing? It's just a constant. It's something to do with coordination. It's a coordination constant. We've talked about this before. When a reaction occurs, the reactants have to find each other. They have to collide. But they have to collide in the correct orientation. That's what this constant A tells us. It's a function of how frequently the reactants will come together in the correct orientation. This is your standard definition of E. When you're talking about natural log, the difference between base 10 log and natural log, base 10 log is raised to the power, is raised to 10, the 10 raised to the power. This is E raised to the power. This comes about naturally. Here's your activation energy. R is your universal gas law constant. But it looks a little different because the units are different. This is another one of those examples where R can look very different in very different situations, but only because we're using different constants, different units. We're using different units. So instead of liter atmosphere per mole Kelvin, this is joules per mole Kelvin. T, of course, is your absolute temperature. And I want you to notice this negative sign right here. That's a significant negative sign, because I can rewrite this without that negative sign as a constant divided by e to the positive EA over RT. It doesn't look as pretty. It's much better in this version. But I do this for a reason. If EA is large, okay, the larger EA is, the larger this becomes. And the larger the numerator is, the smaller the value of K, the smaller the rate law constant. So, and it's easier to see that when I rewrite it in this format. It's easier to see that. I can see it here because I'm so used to looking at it. That negative sign there kind of messes students up from time to time. But when EA is large, K is small, which means that the reaction rate is going to be very small. So when you look at that diamond turning into graphite, is it turning into graphite? Yes, it really is. But the activation energy is so large that the reaction rate is excessively small. The other thing I want you to notice is that we have a fraction over a fraction here. This temperature is at the bottom of this fraction. The larger this temperature, the smaller the fraction. So as temperature goes up, the power to E goes down. Temperature goes up, this power goes down. And as the power goes down, this becomes smaller. And as this becomes smaller, as temperature goes up, that means the rate law constant goes up. The higher the temperature, the higher the constant K, which means the rate will be faster. This has a couple of interesting implications. For the reaction, the activation energy, yes, it's important to know what it is, but it doesn't change. It's constant. The only thing that changes in here, in the Arrhenius rate law, the only thing that we can vary ourselves is temperature. That's all it is, temperature. As a basic rule of thumb, and these rules have many, many exceptions, but as a basic rule of thumb, chemists know if you increase the temperature by 10 degrees Celsius, you approximately double the rate of reaction. Every 10 degrees Celsius increase, you double the rate of reaction. As a general rule of thumb, when you put something in a refrigerator, you are lowering the temperature by about 10 degrees. That means that when food goes bad, it'll go bad in the refrigerator. But generally, it will go bad in the refrigerator. It will last about twice as long in the refrigerator as it does on the counter. The reaction doesn't stop. It doesn't stop in the freezer either. It doesn't stop. But you slow down the reactions. You slow down the reactions. I have meat. Okay, that has nothing to do with what we're talking about. Oh, wait, I can make it have something to do with it. I have meat in my sink. I took it out of the freezer today and I'm thawing it out because I think I'm kind of in the mood for a shepherd pie. My friend's going to yell at me and say, it's a tater tot hot dish. It's a shepherd pie. I just don't want to make the potatoes. Anyway. And she will yell at me because it's at room temperature right now. It's thawing out. And she'll say, well, you're not supposed to let meat go to room temperature. Well, you really don't want to let meat go to room temperature and then refreeze it. I'll tell you that. But the same reactions that are going to happen at room temperature are going to happen in the refrigerator. The reason we put meats in the refrigerator is twofold. First of all, right now, that heat is being wasted. If I put those frozen meats in my refrigerator, it would help me to keep my refrigerator cooler, which will save on my power bill. So yes, that's a good reason to put meats in the refrigerator once they come out of the freezer. And yes, I do have to use that meat a lot faster, about twice as fast from my sink than if it's in the freezer. So the same reactions will occur, they just occur slower. Kim, do you happen to know what happens to respiration rate when someone is running a high fever?
It's higher. It's a higher respiration rate.
One of the ways you can tell if someone is running a high temperature is if they are more or less panting, if they're very shallow, fast breaths. Do you ever wonder why?
Cooling their body down?
No, it's a good guess. It's a wonderful guess. It's not quite right. It's the Arrhenius equation. Arrhenius tells us why. The collective set of chemical reactions that keeps us alive is our metabolic processes. Those are just the chemical reactions of life, just metabolism. And in metabolism, we produce carbon dioxide. That's one of the byproducts of metabolism. When we're running a fever, look at what happens. At a higher temperature, we did it down here. At a higher temperature, reaction rates go up. When you are running a high temperature, high enough to be significant, when you're running a high temperature, that means that, what the heck did I do? For some reason, my remarkable is rebooting. Okay, so anyway, so when you're running a higher temperature, Arrhenius tells us that our metabolic processes, because they're all chemical reactions, they're increasing in rate. All of a sudden, we are running twice, roughly. We're running significantly faster. That produces more carbon dioxide. So the reason that people breathe faster when they are you synced? Ugh. Well, that's annoying. This did an update, which is why it did that. So anyway, higher temperature, your metabolism is going faster, you're producing carbon dioxide faster, you're breathing faster in an effort to exhale that excess carbon dioxide. And it all boils down to Arrhenius. all the Arrhenius equation. Okay, I'm trying, this thing updated unexpectedly on me. Means now I need to figure out where I put my. Okay, I have to bring my notes back up. Okay, any questions about the Arrhenius equation or kinetics? We're not quite done with kinetics, but now I need to reshare. All right. They say that teaching is simply the art of lying without doing too much harm. I've been lying to you. Kind of. It's a small, it's a sin of omission. Because reactions can be reversible. And if you want to know a dirty little secret, except under rare conditions, almost all chemical reactions are reversible reactions. In our metabolism is filled with reversible reactions. It must be reversible. They must be reversible, because if they're not, we would run through our metabolic reactions one time and expire. They have to be reversible. Anything that is endothermic in one direction is exothermic in the other. Anything spontaneous in one direction is not spontaneous in the other. But well, why not? Your hemoglobin carries oxygen from the lungs to the cells, where it will give up. HB is a symbol for hemoglobin. It's not a compound, it's hemoglobin. It will give up the oxygen, which can be used by the cells. Will give up the oxygen and take the carbon dioxide away. Ooh, that's a good one. I should have done that one. That's okay. But look, that's not the only reaction. If this was all it could do, our hemoglobin would make one pass and they'd be dead. In our lungs, the hemoglobin, which now have the carbon dioxide, will give up that carbon dioxide. Excuse me while I belch rudely. I apologize for that. It will give up the carbon dioxide and pick up an oxygen. Notice that these two reactions are exactly the same, except the reactants here are the products here, and vice versa. This is a reversible reaction. So we can write reversible reactions with this notation. It looks very much like a regular chemical reaction, except now we have this funny double-headed arrow. It's half arrows pointing in opposite directions. That means reversible reaction. When we speak of reversible reactions, we still have reactants on the left and products on the right. But notice that it now becomes kind of arbitrary, because I can choose to write this reversible reaction because it's reversible. I can write it like this. So we still have reactants on the left and products on the right. Which one is correct? That's a good question. It depends on why you're writing the reaction down. Kim, how often in the past week have you written down a chemical reaction just for fun?
0.
Yeah. So why would you write a chemical reaction down? Well, you write chemical reactions down to make a point. If I'm talking about lung function, I'm talking about taking carbon dioxide off of hemoglobin and putting oxygen on it. I would write that one as I did on the bottom. So I might write this one if I'm talking about lung function. If I'm talking about cellular processes, then I'm talking about taking oxygen off of hemoglobin and putting carbon dioxide on. So if I'm talking about cell processes, I might write it on like I did on top. So the way we write a reversible reaction really depends on the context of why we are writing it as we are. Okay? But aside from the fact that it's reversible, it's really no different than any other chemical reaction. It still has to be balanced. Here's a critically important trivial equilibrium. That sound a little contradictory? Critically important trivial reaction. Here's a trivial reaction. Standing in a deli in New York City, the exit was behind me and the refrigerator was behind me, and I was ordering a sandwich, and I said, yeah, charge me for a can of pop and I'll pick it up on the way out. And this woman standing next to me put her hand on her hip and she said, "It's a soda." I looked her dead in the eyes and I said, "No, it's a carbonated beverage." Everyone knows that pop or carbonated beverages are carbonated. Means that basically under high pressure, they force carbon dioxide into water. That carbon dioxide forms carbonic acid, which is the product, as I've written this, H2CO3. Acids tend to taste bitter. So if you've ever had seltzer water, you know it's a very bitter kind of a thing. So in order to get you to drink their bitter, terrible drinks, what do pop industries do? They add a ton of sugar to make it sweet, to overcome that bitter flavor. I'm near the end of this. My carbonation is nearly gone. Well, when the carbonation is gone, we're going in the reverse reaction. By the way, by convention, products to reactants, is the forward reaction. So when they are first putting carbon dioxide into the pot, that's the forward reaction. But after a long time, we are talking about the reverse reaction. So now the acid is almost entirely gone because now it's converted back to carbon dioxide. That's why it fizzes. So it makes it fun and why we all drink it, even though we shouldn't because it's bad for us. It's fizzy. And when that fizzy is gone, the carbonic acid is gone, the bitterness is gone, but what remains? The sugar, which means that that sweet remains. And that's why flat pop often tastes sickening sweet, because all that bitter flavor is gone, but the sugar is still there. This is a trivial application of this reaction, but now let's write a second reversible reaction. Acids are very much like salts. They dissociate in water, but specifically when acids dissociate, they give us the hydronium ion. This is what makes an acid an acid. Get a lot of hydronium ions and you become acidic. When someone hyperventilates, what are you supposed to give them?
A paper bag.
A paper bag. So that it can capture the oxygen, right?
No,
No, what's it doing?
capturing the carbon dioxide.
Capturing the carbon dioxide. But why? Why is it important to capture that carbon dioxide? Because as you lose too much carbon dioxide, you are losing carbonic acid. And as you lose your carbonic acid, you're losing your hydronium ions. As you lose those hydronium ions, you become less acidic. You become alkaline, a condition called alkalosis, which can be very, very dangerous. All of a sudden, you're too basic, not too acidic, too basic. And as your pH rises, your proteins cannot maintain their proper structures to do their function. Your proteins begin to fall apart and your cells begin to die until eventually so do you. This is a critically important reversible reaction. This is what keeps us alive. That carbonic acid concentration that we have in our system helps to maintain the proper pH level in order to be functional, in order to actually be able to work. Okay? Any questions about equilibrium? No, not equilibrium. Any questions about reversible reactions or kinetics?
Nope.
All right. I have 5 minutes left. I think I have time to cover this. Let's talk about equilibrium. And it's probably easier to think of this in terms of pop. We've spoken of equilibrium before. I've given you the definition. Do you happen to remember it? It's okay if you don't, because it's been a while. No observable. All right. The definition of equilibrium. No observable no observable changes over time. No observable, and the two keys observable changes in time. Now, here's something that I want you to know about reversible reactions, and most reactions are reversible. We just learned that our rate laws are all based on concentration. Rate laws are all based on concentration. So as you force more and more carbon dioxide into water, you're producing more and more carbonic acid. That's high pressure. Now we change the system, we take the cap off, the pressure drops, the carbon dioxide begins to fizz out, and what happens? The carbon dioxide concentration goes down, which reverses the reaction, and you're speeding up the reverse reaction. But when you are capped, when your pop is still capped, the carbon dioxide reversible reaction does not stop. This reaction is constantly occurring both in the forward and reverse reaction, in the forward and reverse direction. In this capped system, you still have carbon dioxide dissolving into the water. Okay? To form carbonic acid. But the more carbonic acid you have, the faster the reverse reaction will go. So the carbonic acid is breaking down to form carbon dioxide. If we imagine a situation where we had absolutely pure water with no carbonic acid, that reaction of breaking down would be zero because there's no carbon dioxide, carbonic acid to begin the reaction. But as more carbonic acid forms, the rate of reaction for giving carbon dioxide off increases. So what is equilibrium? Equilibrium really occurs, and I'm talking about any kind of equilibrium. You're really at equilibrium when the reaction rate in the forward reaction equals the reaction rate in the reverse reaction. If I make $325 a month, which is about what corporate USA is paying people these days. If I make $325 a month, but my bills come to $325 a month, don't we wish? How much money am I making each month? Nothing. The same amount of money going into my bank account is the exact same amount of money coming out. I'm not going up. I'm not going down. I'm at equilibrium. Does the money exchange stop? No. The money exchange continues. Absorbing carbon dioxide to form carbonic acid is still occurring. And the breakdown of carbonic acid into carbon dioxide is still occurring. But at equilibrium, those two reactions are occurring at exactly the same rate. That is equilibrium. And okay, I'm still recording. That is pretty much the end of the lecture. I thought I clicked the wrong thing again. Last time I clicked the wrong thing to cut myself off. Anyway, that's pretty much the end of the lecture. I need to check my notes and see if there's anything I've skipped because there are a couple of questions I have. But we're going to continue this next week on Tuesday. Any questions, comments, issues, complaints, problems, money you'd like to give me?
No.
Figures. All right. In that case, thank you so much for attending, and I am out of here.